Today we are going to do section 4.4, page 389. And let's look at the definition of a tangent plane. What's a tangent plane? Well, it's something like this, okay? Now let's look at, here's a surface, okay? And then we'll stick a plane on it and touch it at, if it is possible to touch it at just one point, then this is the tangent plane of the ball at any point that it touches. Okay, it only touches at one point theoretically. So, in other words, this is very much like the tangent line in the two-dimension, the curve that we learned before, right? The tangent line is the line that touches the function at one point. Tangent plane the same way. It's the plane that touches your function, which is in 2D, at one point. Being that we are working on 2D now, the tangent line is now evolving into the tangent plane. Now remember that the fact that this tangent plane is showing it the way this doesn't matter. Because what I mean is, you're in a curve in one dimension, okay, this is your tangent line, right? But it doesn't matter how it goes. For example, your tangent line might do this. Okay, and the same with the plane. The surface might go up and then stick out, and the plane actually cut right through it. It doesn't have to like touch it and then take off and never see it again. It can cut right through also. Either way, the point is the situation is exactly the same. It's just that now we're dealing with 2D. I mean 3D in 3 dimensions. So that line becomes our plane. Now let's look at the definition in the book that gives on this page of what is a tangent plane. Let P0 it be a point on some surface and C be a curve that passes through the P point and lies entirely on the surface. Fine, okay. So you draw a line on the surface that passes through the point we care about. Now, if the tangent lines to all such curves at this point lie in the same plane, then this plane is called the tangent plane of S at P. Now, if this sounds confusing to you, please read it a few times, maybe a couple hundred times until you understand it. But the point is that when you think about it, why wouldn't all the tangent lines lie in the same plane? Because as you can see with my ball, then the tangent line obviously lies in the same plane. But it happens when your plane has inconvenience like this. If it has a fold in it, then the tangent line kind of get all screwed up. For one thing, the tangent line might not even exist, okay? And that at the point, at that particular point in question, and when that happens, then yeah, you got a problem. So see, like this, I have a fold here, and now the thing isn't smooth anymore. It has a sharp area, and so then the tangent plane doesn't exist anymore because you folded the paper. But most of the time, we're not going to deal with that. Those are just exceptions. And in general, we are going to the next thing, now that we know there's such a thing as a tangent line, we are going to calculate the equation of the tangent line. So you're going to be doing exactly what you did in Calculus 1 back in the day when you did find the tangent line and the equation of the tangent line to the given function, blah, 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 right? Now you're going to be finding the equation of the tangent plane to the given function. Now, what was the equation of the tangent line again? It was done with the point-slope formula, okay? The good old point-slope formula that in calculus you've used about a zillion times. And to remind you, here is the point-slope formula, right? Which is, the point-slope formula means z equals the original point, and then plus the derivative, okay, of the value, and then y minus y0, that sort of thing. And in 2D, that is exactly the same formula. Now look up a little bit. Excuse me. Look up a little bit right here, where we have the tangent plane formula. As you can see, you have the value of the original point plus the derivative on the x, partial derivative in the x direction, x minus x0, and then partial derivative in the y direction, y minus y0. So it's identical to the original one, except that now you got the y direction added, which makes sense. That is, so it's a slightly longer, but the same process or similar process. Now, to prove that how this fact is true, what we're going to do is look back as to how to find the equation of the plane. Now, remember how the plane equation is found? If you don't remember, just go back to page 195, okay? Equation of plane. What was the equation of the plane? N dot PQ equal to 0. Now, what does that mean and how does that translate? Go look at that page and you will refresh your memory if you don't quite remember. And is actually a simple matter of finding two vectors, okay, in the direction of each tangent line, and then you do the cross product and so on. And then you do the dot product, and there's your plane. Is similar. We've done various homework doing exactly this thing, so I'm not going to go over it, and I'm asking you to do this as part of your homework, being that we've done this before, okay? Like many, quite a few problems in the planes back in page 195. So please do this. I just want to mention one thing is what are the two vectors? The two vectors, you don't have to, you can just find 2 points on the line and then subtract to get the vector, or you can just consider the fact that the two vectors, being that you have two lines here, and the two lines is, first let's consider the first line. The first line is is z and y, okay? So the first line is in the zy plane, as you can see, the equation of the first line, up there or something is a straight line. So what you're gonna do, what the book did, is we'll take a vector down here that has the same, that it goes j this direction, okay? Here's j, and then k, it will go up by the derivative, that is f of y, which is the derivative at that point. Now, if you do fyk, now if you do that, then this is unit 1. So then the slope of this thing is f of y, which is exactly the slope of the original tangent line along that plane, which means that you can use this vector right here to calculate your cross product. Yep, and that's that. So that this line I should mention is, did I forget to mention that? What was this line again? This line is the tangent of the vertical trace given at x equal to x0. Okay, so in other words, on the x plane we have that line, that tangent, and then you will find the vector that represents the tangent and then cross it with the other one. Now so please do this as part of your homework. Now, by now, you can see why we take partial derivatives. The partial derivatives are simply the derivative in two random directions, right? X, that happens to be the x coordinate and the y coordinate. But in doing that, just by doing that, however, we're able to determine two tangent lines, right? The two tangent lines, from that we can get two vectors from which then we can define the plane. Because two crossing lines that's not parallel will define a plane. And that plane is actually represents everything. Basically the entire tangent plane of our surface, which is why we do the partial derivatives, see? Because we only require two, and then now we know everything, the entire plane, which way it goes, and most importantly, we know which way is the steepest descent. Right? Because we have the plane, and we can look at the plane as which way is this sloping, the fastest slope down, and all those things. In fact, we know which way does it slope every single direction. So just from knowing partial derivatives, now we know the slope every other way too. So having said that, please do example 4.21. And next, more 4.22. Same thing. You just take the derivatives, plug it into the formula, and then you're good. And then the next thing, of course, we're going to look at something that doesn't have a tangent plane. Why? Probably because it's got a fold, like I showed you earlier. If there's a fold, how are you going to calculate the plane? So let's look at page 390. Let's see, where's my pen? Oh, let's look at page 393, where we see there this example of no tangent plane because it's folded there. Now, 393 example, you have some function that has two parts. They usually do, right? And a function defined by two parts, where the reason is because, as you can see, the problem exists as 0. Everything else looks good. Now, as 0, this function does go to 0. Okay, so then we define it as 0 when x and y equal to 0. The problem is, however, it has an odd behavior there. Now the book shows you a graph, okay, and I think that's not the best angle to show it to you because you can't really see what's wrong with it. What's wrong with it anyway? It's not that obvious. So please type this function into the decimals calculator, and then you can see exactly what's wrong with it, because then you can turn it around and all that. Now let's see, I typed it in, and as you can see how to type it in, you just type it in like it is. XY, you might need it in parentheses, and then the division line, etc. Or you might not actually. Division, just type the whole thing in, including the z equals. So once you type that in, this is decimals 3D, and then here's your graph. As you notice from a different angle, there's the distinctive V shape. Okay, in other words, there is a sharp point. There is no way that you're going to stick a tangent line there that fits everything. So that is why this particular function doesn't have a tangent plane at the origin. Let's see. And yeah, see, the book later says if you let x and y be equal, along the line x equal to y, so you have f of x and x, you plug it in, you realize you end up with the absolute value of x. The absolute value function, as you remember, is that V-shaped thing, right? And which is why that's also included in the graph of the function itself. See the V-shaped thing right there, along there? And even though the function contains both x-axis and the y-axis, if you look at it carefully, yeah, and when x equal to 0 goes right through the surface, and so does y equal to 0 or something like that. Is it x equal to 0? Whatever. The point is, the x-axis and the y-axis are included in the plane, but then it start, folding and twisting, well, not twisting, but folding. There's a corner there, a slight fold, which messes things up. So not all functions have tangent planes, or should I say not everywhere in a certain function has tangent planes. The rest of the function, besides origin, as you can see, is fine. You can stick a tangent plane because the rest of it is all smooth. There's no corner or whatever you call that. So that is how that goes. And next, let's look at linear approximations on the following page. This is page 394. What was linear approximation? That just means some quick approximation of a function. That is, you use the tangent line, okay, to approximate the function with values that's close to it. Here's the equation of a tangent line, and then you use that to plug in values that's not at the point of touch, a point of contact, to approximate the value of the function. The reason for doing that is for applied math, such that if you don't actually know what the function is, but for some reason you know the derivative, okay, so then you can approximate what happens in the future because you don't actually know the function itself. But anyway, we've done that in Calculus 1 for one-dimensional functions, and guess what we're going to do now with the tangent plane? We're going to do it with the two-dimensional functions, okay? And the approximation is exactly the same as in Calculus 1. You have a look down at the definition. You have you use the tangent plane to approximate some area next to it. Next point, okay? And this is the equation of the tangent plane, which we will change it to be the linear approximation. And so you use the plane and plug in values of x and y around it to calculate your approximation of the function. Okay, so with that, please do example 4.23 as part of your homework. You just plug numbers in, really. There's not much to do here.